I'm R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this video, we are going to discuss the topic on synchronous counters for the unit shift registers and counters. And this is for the course Digital System Design. So the contents of this presentations are, first we are going to see a recall of the previous topic, ripple counters, and next we are moving to synchronous counter basics. We are going to see the parallel operation, simultaneous clock signal, and counting of this synchronous counters in design thinking way. And also we are going to see the real world applications, circuit architecture, and also the implementations. So finally we are going to see the summary part and assessment to know the level of understanding. So now the previous topic, ripple counters, is asynchronous counters. In synchronous counters, a common clock signal is applied to all the flip-flops simultaneously, but in ripple counter or asynchronous counter, only the first flip-flop receives the external clock signal. The output of one flip-flop is given as a clock signal to the subsequent flip-flops. So, and because of this reason, the ripple counter design is very simple and cost low. And the limitation is due to this ripple operation, because of cascading of clock signal from output to next flip-flop, a propagation delay occurs, and this limits the speed. So this is suitable. Ripple counter is suitable for only low speed applications, and for high frequency and high speed applications we need another circuit called synchronous so the synchronous counters, a common clock pulse is applied simultaneously to all the flip-flops, which eliminates the ripple delay. And because of this reason, synchronous counter is more suitable for high frequency and high speed applications. So the empathy part of the previous ripple counter is it's a low speed operation and not suitable for low frequency applications. And this is overcome with the synchronous counters. And synchronous counter use the flip-flops are synchronously connected with common clock pulse, and its advantages as reliability, accuracy, versatility, and the speed of operation is very high. And if we compare the asynchronous and synchronous counters, the key differences are ripple counters. There is a sequential processing because of cascading structure, and this leads to delays. But this design is simple. And if we come for synchronous counters, the simultaneous processing increases the speed of the operation, but at the same time the complexity also increases. So now coming to the ideate part of design thinking, the working principle of this flip-flop. So here D flip-flop is taken. So when the clock pulse arrives, which is given by the master clock pulse, all the flip-flops receives the clock pulse simultaneously. And next is the logic gates check whether the conditions are met based on the previous state, and all the enabled flip-flops operate simultaneously, which enables the parallel transition. And now if we compare the operation of synchronous counter with design thinking process, the empathize part is identifying the problem, that is the need of fast counters without ripple delays, and define part we are creating the timing or state diagram, which is mapping of all required states and transitions. And ideate and prototype time, we use K-map to derive minimal logic expressions, and from the minimized expression we can design a circuit which is having the flip-flops for synchronous counters. And there are different types of synchronous counters. One is the binary counter, which counts in binary sequences. Decade counters counts only from 0 to 9. And there are up-down counters are available. Up counter, The sequence are counted in ascending order, but in down counted it is the reverse case. And the ring counters, Johnson counters are uses the feedback mechanisms for counting. And the applications of synchronous counters are, they are useful in programmable logic devices, frequency dividers, also useful in digital clocks because of the counter operation, and microprocessor event counters are other applications. So far we have discussed about the synchronous counters and its comparison with asynchronous counter, advantages, disadvantages, design thinking impact, and also the core components needed for the circuit architecture. So now the assessment questions and the ripple delay. So why there is no ripple delay? Because all the flip-flops are connected with the clock pulse simultaneously. So there is a parallel state transition which eliminates ripple delay. There is zero ripple delay in synchronous counters. And maximum frequency difference is synchronous operates 5 to 10x faster and no propagation accumulation. And when to use synchronous is for high speed, high frequency applications, precision timing, address generation, digital clocking requires speed and accuracy. So this is about the ripple counters in design thinking approach, its operation, need, applications, advantages and disadvantages. References. Thank you.